The core and laser projects. Let's first spend some time reading this introduction paragraph here. Earthquakes release different kinds of waves. These waves shake the ground in different directions. Some shake side to side, some shake up and down. These different waves can be detected by tools called seismometers around the world. On the next page is a circle that represents Earth as seen from above the North Pole. Suppose an earthquake occurs in England at 0 degrees longitude, which is represented by the black dot. So here's the North Pole of the Earth, looking down on the Earth. Here is England at 0 degrees, England with the black dot. The quake will send out waves that can be detected thousands of miles away. The open circles show the locations of instruments around the world. The table below shows whether or not each station felt the S wave from the quake. Procedure. If a station feels the quake's S waves, draw a straight arrow from England's black dot to the station's open circle. The first couple are done for you. So on the table here we have Poland being at 20 degrees longitude, and it did detect the S wave. So we have a line going from the black dot over to the 20 degree mark on the globe. And then Turkey is at 40 degrees. It has, yes, it did detect the S wave, so we have a line from the England to the 40 degrees longitude of Turkey. Iran at 60 degrees felt it, so we're going to draw a line there. India at 80 degrees, it felt it. Let's see, next, Vietnam at 100, it says yes. At 120 degrees, we have the Philippines, but it did not feel the S waves. So we're not going to draw the line there. In fact, the other stations, Japan, Kamchatka, Bering Sea, Hawaii, they did not feel it, nor did Alaska or the Western United States. We have to go all the way over to the Midwest at 260, way over here. So I'm going to draw a line from England to the 260 seismometer station. And then we can draw it to, let's see here, the Eastern United States and Newfoundland at 300 and Greenland at 320 and lastly Iceland at 340. So these lines here are all the different paths that the waves of the earthquake must have taken from England to these different seismometers. Something is in here that blocked the waves from hitting these other seismic stations over here. So, let's read this. The opposite side of Earth does not feel the quake. There appears to be something in the middle of the Earth that blocks S waves. This is the outer core. Shade in the biggest circle centered in the middle of the Earth that would block the waves that we see. It is the biggest circle that fits between the lines that you drew. So here's the lines that we drew, and here's the circle that just touches there, and then over here just touches there. So this is the biggest circle centered on the North Pole here that fits between the lines that we drew. So we're going to shade that in. It says down here, S waves move side to side. They can't move through liquids. Since the outer core blocks S waves, geologists believe that the outer core must be a liquid. Okay, now then, number one, find the diameter of the outer core in centimeters. So that is going to be what we shaded in. Put the 0 mark over here and over there. I don't know if you can see this very well. It's right there. There, it's in focus. Now you can read where my pinky is pointing. That's how many centimeters the diameter is. Line number 2. If 1 centimeter is 800 kilometers, how many kilometers does your answer represent? So take the number of centimeters that we just saw on the ruler, and you're going to multiply by the 800 here. Each centimeter is 800, so you multiply our reading by that. And that will be the end of the core portion of the lab. Now let's move on to the laser project. Task. We're going to see how light waves bend when they enter different materials. Relevance. Light waves act the same way as earthquake waves. Success. You will measure the angles that the laser makes as it enters glass. Warning, do not shine the laser at anybody's eyes or face, including your own. Place a triangle on the map as shown by the outline. You may need to move the glass to read the center circle numbers. Okay, this is continuing from the previous 2 questions on the course. So question number 3. Shine the laser down the path labeled initial path. It hits the glass block at what angle? So let me get this stuff here put together. I should have done this earlier. Sorry, I didn't. But there is the prism, and here is the initial path right there. You need to read the protractor here. Where does it cross? Let me zoom in here a little bit. It is between 30 and 40. The exact number you're going to have to read. Okay, now let's get the laser going. Okay, here's my laser, and I'm going to shine it right down. Oh, there we go. Shine it down this path. And when I do that, where does it come out? We can see it's shining on my finger right there. So what we need to do is to read this number right there. Let's zoom in on that. It's going to be this number right there. It is bigger than 20, but it's less than 30. You're going to have to estimate that on your own. That, let's see here, would be described as path C. That's question number 4. Question number 5 is the number that you just read here between the 20 and 30. Number 6. From this activity, we learned that when light waves enter different materials, they choose option A, B, or C. Now, continue reading the bottom part of your page here and go on to the next page as well. And that will be the end of this video.